All right. So chapter 3 is going to be on decay rates and cross sections. Unfortunately, it doesn't start you there. Unlike Griffiths, it starts you off at the Fermi's golden rule, which is something we just started talking about at the end of last chapter and beginning of this chapter. Okay. And remember that Fermi's golden rule, at least at this junction, right, is this idea how you can calculate transition rate from some initial state to some final state. And I think the example I was trying to give on Friday was if you have some, let's say, a hydrogen atom with like different energy levels, right? This is not the greatest example, but hopefully it's more familiar, okay? Where you have, some electron going from n equals to 3 to n equals to 2 state, right? These are different energy states. So the Hamiltonian of this particular atom is changing, right? So you're going to have some changing Hamiltonian, and that changing Hamiltonian is this H hat prime thing, right? This is a time-dependent Hamiltonian, right? Okay. And the way you figure out pieces of this gamma Fi, right, or the transition rate. So just think about transition rate when you see this, right? I don't know why it will be the letter gamma, but transition rate, right? Think about that. Okay. Right. You have a 2 pi. Hopefully we can all calculate 2 pi. Is this TFI thing, right? TFI is this transition matrix element, which is basically like a to first order. Let's just not worry about this part for now. That's the second order. Okay. To first order is basically the, it's kind of like the expectation value of that Hamiltonian with this initial and final state around it. Okay. 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 And what we're going to see is that each of these little expectation, actually they're called correlation function between the initial and final state. Okay. They are actually going to be associated with different Feynman diagrams. So each of these will have a different Feynman diagram attached to it when we get to hoping for the 2 weeks from now, we can get to it when we can actually get into quantum electrodynamics. Okay. All right. But then there's the other factor here, and this is what we're going to deal with here, this rho, right? You guys remember what it was called? Supposed to take care of density of states, right? Right. This density of state thing, okay, and density of accessible states, yeah, but density of states overall, yeah, it's just some number, right? Okay, and Thomson goes through, to kind of derive for you why this density of state you can rewrite it as kind of like the total derivative of the number density states, the number state density. There's a lot of densities around. Number of, this is actually the number of particle density. Okay. Okay. Right. With respect to the energy, but then evaluate it at its initial energy, because, right, at the initial energy, that's when the particle started at, right? Whatever that change is allows you to change into a new regular, you can even put in the F here, right? There's some final energy state that you're transitioning from E initial to E final, okay? Right, and this is the idea of where we start looking at these weird functions, right? Where I think last time I should have copy and pasted it, where you have the sine square over x function, right? Where you have some ripples up, right? Where it is most probable for the particle to be in its initial state, but then what's going to happen is that there's some probability for it to transition out of that, right? Where especially, if the energy is very close, right? The final energy is very close to the initial energy. That means you have some width here. And also, there's also these sine square oscillation that you'll see. Okay. Okay. What this allows us to do is basically change this equation into this thing called a Dirac delta function, where the direct delta function, so there is a description of it in the appendix A of the textbook of Thompson. Appendix A of Thompson. Is pretty mathematical, but it gives you all the equations you need, basically. Okay. And the idea of a direct delta function is that it's a function that is zero everywhere except for a single infinitesimal point, and where it's infinite. Okay. So this function actually makes no sense at all, but it allows us to do this math trick where, well, if we're integrating over this direct delta function, right? If the limits of our integral, let's say y1, y2, right, is between, right, this x naught, that means that integration is going to integrate to 1. But if let's say I'm integrating from y2 to y1 here, where it doesn't include this peak, right, that means you're going to get integral of 0, right, because you're adding up 0 things all the time. Okay, where this infinity, basically you're multiplying infinity. Well, you have infinity divided by infinity, you get 1. Okay. Okay. Math people will yell at us, but it's okay. They're not here. Because infinity divided by infinity is not 1 all the time, right? It could be anything, actually. It's undefined. But in this case, we're going to define it so that when you do this integral, you get 1. Okay. Okay. So what this is imposing physically is that, well, whatever the initial energy is minus the final energy, right? If they are basically almost the same, then you get something that's non-zero. But if not, then you get 0, right? This imposing kind of this graph that we just draw here, right? This was the sine x squared graph over x squared, right? Okay. Okay. Now, right, we have this little delta function thing in here. Now we have just to deal with this dn thing. I'm going to hopefully get to this dn thing in the next section here, okay? So the main point of this first section is to just to think about, well, the transition rate can be calculated from the Fermi golden rule. We've been talking about that multiple times, right? We're going to have to determine this matrix element TFI, right? If you want to write it nicely with a subscript, okay? And this density of state function, right, is a condition that makes it so the nearby energy state is the most probable transition, right? The closer the two energy is, the more probable you're going to get, okay? And this turns it into some delta function times dn, okay? Just doing a lot of rearrangements to set up things, okay? All right. Section 2 is actually where we get to actually determine what this dn thing is, right? This differential in the number of particles, okay? Okay, right? So in this section, we're going to write this dn in the form of differential and 3-dimensional momentum instead. So instead of doing dn, we're going to turn this into some three-dimensional differentials in momentum, okay? That way we can actually apply conservation of momentum to the interaction, okay? Because remember that, you know, let's say we have a particle decaying, some A particle, right? It's going along, and it's going to decay into 2 things, 1 and 2, okay? So we can track the particleness of it, okay? What's happening is that, right, you have some momentum of A coming in. You can even think about this as a 4 momentum or 3 momentum with or without the energy as you like, right? Okay, and then some momentum 1, momentum 2 coming out of these 2 particles, right? So the energy part, right, is constrained by this delta function of energy, okay? This number density thing is going to be constrained by the 3 momentum, okay? So we're going to try to figure that out. Okay. Well, I'm going to kind of skip through the section to show you how it actually came about, okay? Okay. So remember this TFI thing that we were talking about is always the psi square, has to do with the wave functions, right? The psi square, psi 1, psi 2, psi A, right? In that particular order in this case. Don't worry about this part too much, okay? But, right, these wave function, right, has some amplitude and then some oscillation wave in the in momentum space, right? Px P dot x minus E times t, right? But this normalization in front here is arbitrary, right? And typically what we want to do is actually normalize this wave function so that it has one particle in some box with a length a in all the sides. So what you're doing is you're putting there's on average one particle in this little box, okay? This makes things easy because if you were to do the integrate all of the probability of finding this this particle in this box, you by definition it's one because you put one, you're normalizing it so there's one particle in each of these boxes. Okay, this may seem really arbitrary, right? But it's just very convenient. And in the end, what's going to happen is that this is going to scale with just the number of initial particles and what you're actually calculating is kind of like the percentage instead. Okay. What this allows you to do is then, yeah, that's just the math part. That means, let me maximize this. Okay, left, right? That means, right, on the left-hand side, right, you have a to the third power, right, just from this triple integral, right? That's just the volume of that box, okay? And then a squared comes from the two wave function, right? They multiply into each other. Or the e to the I px minus e, sorry, e to the I p dot x minus e minus t, e times t, right? They just multiply to e to the 0, you get 1 from that, okay? Right, that means the condition you can impose is that, well, whatever this amplitude square is, right, has to be 1 over the length of each of these cube sides squared to the third power. In other words, 1 over the volume of your cube, okay? So bigger the amplitude, the smaller the volume, okay? They're inversely proportional to each other, okay? The other thing you can also impose, this is going to be useful if anyone doing condensed matter with this also. Okay, someone found something on Zoom. Okay, I'm not going to say what. Okay. The other thing you can impose on this is that, right? Let's say this is the x-axis, right? Okay, this is the y-axis, right? Whatever the wave function is here, it's going to repeat itself by the time it gets to the other side of the box, okay? Because it has to kind of keeps going around this box, okay? This is a periodic boundary condition where whatever psi is, right, in at x or y, z, if you add a to one of the coordinates, right, you should get the same thing, okay? This allows you to quantize the momentum, meaning that each of these only certain momentums of particle waves can actually fit in this box, okay? And this is what allows us to quantize the number of particle within each box, okay? Right? And this is I think it's a good picture that when I was, not from this class actually, it's from my condensed matter class. And I'm going to try to explain it. And if you don't 100% understand it, it's okay, because I didn't either when I was taking this, the condensed matter class, okay? So the idea is that while you have some 3 momentum of your particle, right? And each of them, right, has to fit in some wavelengths. So this is actually the wavelength, right? With some index n, nx, ny, nz. So these are just 1, 2, 3, right? Blah, blah. Same thing with y and z, okay? So that means, you know, the higher these n numbers, the shorter the wavelength, okay? That means more periods of the waves fit into it, okay? But this also implies that, well, you know, these waves can be kind of shifted to think, instead of thinking about it spatially, you can think about them in terms of this momentum space instead, okay? And this is what we're going to call phase space, okay? When people say phase space, you know, just associate the P with momentum, and then you see that, oh, it's phase space, right? Okay. And since we're dealing with multiples of these momentum, each of these momentum takes up kind of like a 1 cube in this phase space, okay? This allows us to basically think about, well, if we take these and decrease it until you get differentials of them instead, right? So this is a px by py by pz size. Oops, py goes this way, right? Cube. You can shrink this cube into two little tiny bits, right? And then now you have basically this three-dimensional differential in momentum, right? Where it's just dpx, dpy, dpz, and the shorthand for this is just d3 with the capital P. Okay, so fine, not the capital, the boldface P. So the book doesn't do this, but you can draw the vector in if you want. Okay, and this is going to be constrained to some 2 pi to the third power. That's just coming from the conversion from wavelengths to momentum, and then the volume of that box. Okay, divided by the volume of that box. Okay. This is interesting because what's happening is that just like the energy, right, where you have to conserve energy because so that the energy states that are closest to your initial energy is the most likely to find you'll transition to, right? Similarly, let's see if I can do a different color. Okay, so that's why this was useful. Okay, let's do two blacks. Let's do a red here. Okay, similarly, right, in order to conserve momentum, right, you will also find yourself within some kind of thin shell of momentum in 3 dimensions. Imagine like a sphere, just like imagine like a basketball, the leather part. I don't know what's that called, the skin part. So it actually made of skin. The whatever the material of the basketball is made of, right? There's some thin shell, right? And that's where the momentum would most likely get to, right? Because you're trying to conserve regular momentum also, not just energy. Okay, and this is where I'm going to skip. Okay, sorry, this is where I'm going to pull a Griffiths on you. Okay, this is where now, well, if you think about this, the density, these density of numbers of particles flying around, right? You can think about those as just the product. So this summation, this is a product, right? So if you have 3 particles, right, this will be 3 P1, right? To the third, okay, dp2 to the third, right? All these are doing the differential for each of the particles -1. Okay, so remember, look at this as remember this -1. Okay, because what's happening is that you're imposing conservation of momentum. So momentum coming in has to be equal to momentum coming out, right? In 3 dimensions also, right? So these two are what's going to be accounted for. Okay. Oh, I already wrote it down here. Oops. Okay. Where this the incoming momentum is constrained by yet another delta function. Okay. Okay. Where we're making sure that the momentum coming in minus all the outgoing momentum, I can get rid of this white thing. Okay. It's going to add up to 0. It's just to apply conservation of momentum. Okay. Right. And that's what this dn thing turns into. Okay. You got some 2 pi to the third power just from converting wavelengths to phase space. And each of these factors will also give you a 2 pi to the third power on the denominator. So in the end, you actually end up with 2 factors in this case. Okay. And then you're going to have to somehow integrate, and supposed to integrate, instead of integrating over dn, you're going to have to integrate over momentum instead, which is doable because we can actually measure the momentum of the particles coming in and out of our little box, right? Okay. So to summarize this section, right, we're going to have another piece, right, of our Fermi's golden rule where we can calculate this density of state dn thing, okay? And this delta function up here, delta functions are actually really nice. So it actually allows you to compute integrals because the integral of the delta functions is 1 if the peak is actually within it, right? Okay, so this this delta function enforces this, nearby momentum states are the most probable once again, right? There is a couple of interesting things. Okay, one thing is that, let me erase this, a lot of the stuff. Okay, this product here, right? Oops. Okay, depends on how many particles we're dealing with, right? So if we have a decay, right, 1 and 2, this product will have 2 factors, okay? But if we're dealing with scattering, let's say A, B, scatter to 1, and then maybe exchange some boson between them, okay? Now there's 4 particles. This will give you 3 factors on that product, okay? Why is that a problem? Anyone wants to chime in? Or just reading down there? Yeah, well, the units of dn changes, right? Right? When you have 3 momentum, when you multiply 2 momentums together, right, you get GeV squared. When you multiply 3 different momentums together, you get GeV to the 3rd power, okay? And what we're going to do is we're actually going to try to fix this on the other end with the TFI instead, okay? So just to kind of keep track of these units of GeVs in the momentum, okay? Okay, so there's going to be another factor in the TFI that we're going to have to deal with, okay, that we're going to try to find the correct units for TFI also, okay? So most of the time, I think all the calculations we're going to be dealing with is either a decay or scatter. So you either have 2 factors of momentum or 3 factors of momentum, depending on which process we're dealing with. Okay. The problem is that when you have like the second order stuff that we're not going to deal with in this class, maybe you have to deal with in the future, then you have to keep track of how many factors of P's momentums you're dealing with, right? All right, so basically, right, if you read Griffiths, he just props this down and then you're good, okay? He didn't tell you where it comes from or why it's like that, but that's where. So I'm trying to do the middle thing where I'm describing what Thomson is doing without doing all the algebra steps, that's all, okay? All right, any questions about this? Okay, this little factor here, the density of state factor. And now we're going to have a little thing that kind of annoys me and kind of confused me, but this is how it was historically done. So we're going to do it this way. Try and maximize. So what happened is that, right, this box that we made up with all sides A, okay, it's not Lorentz invariant anymore, right? Right. If I was going on a different frame of reference, let's say traveling to the right at some velocity beta, right? What's going to happen is that I'm going to have length contraction along that direction, and all the stuff will be contracted in one direction. So the volume of this is not Lorentz invariant anymore, right? And so this 1 is actually going to be, right, 1 over gamma instead. Okay. But instead of trying to fix it with this density, because this part came from the density of state, right? Instead of trying to fix it with the density of state, we're gonna fix it with the TFI stuff instead. Okay, right? So previously, what we did is we normalized the wave function so that it's equal to 1, right? So whatever this is, right? Psi star psi, okay, d3x, right? We normalized it to 1. Okay, now we change our mind. Okay, we're going to normalize it to 2 times the energy, okay, of that particular particle, whatever that is. Okay. Okay. So essentially what's going to happen is that, right, instead of just having TFIs, okay, every time you do a integral of psi star psi, you're going to get a factor of 2 times energy of that particular energy, okay, whatever that factor is, okay? So the TFI is the non-Lorentz invariant, okay, matrix elements. But then the scripty, I'm going to try to write it. Well, it's down here on the left here, but usually it's written in this little scripty M. MFI, this is the Lorentz invariant version of it. Okay. Okay. And then we'll have a little homework for you to prove that if you just multiply this wave function by 2 times its own energy, then you will get a Lorentz invariant instead of a non-Lorentz invariant. Okay. So if you normalize this wave function to 2e, okay, and since there's 2 factors of a's in here, right? So therefore, the normalization factor you want is actually 1 over. Let's see. The normalization factor is actually square root 2e instead, right? And that's where this 1/2 power comes from. Oops, sorry about that. Things, right? Does that make sense? This is where I'm jumping a lot. Okay, I jump over this entire section. Okay, but we'll have one little homework problem on that. So just so you can show that 2 times e, if you normalize the wave function to, actually it doesn't have to be 2. It can be anything times e, you will get the Lorentz invariant. Okay. Almost home. Okay, now, right, now we have a new version of our Fermi's golden rule where we're calculating the transition rate from some initial to some final state. There's a bunch of factors of 2 pi's everywhere. So, keeping track of that, you basically have this is for a decay of A to particle 1 plus particle 2. Okay. So this powers of the 2 pi's will change based on how many particles are involved. Okay. Okay. Because of these factors of energy in front of our TFI, if we want to substitute in MFI instead, you get, this, right, instead, right? E1, E2, E3. You get these factors in the denominator instead, okay? And that's where this EA comes from. It's from the denominator of changing TFI to MFIs, okay? Okay. And then that change also brings with it the other energies, right? All the other energies are also in the denominator, okay? It has to stay inside the integral because we're going to have a delta function in terms of the of these 2 energies, okay? EA can be pulled outside in this case because that's just gonna happen to be the mass of whatever particles we're talking about. We're gonna see that in a second, okay? Okay. So that basically is associated with each of these. And these delta functions is going to impose conservation of momentum, right, with our incoming and outgoing particles, okay? In this section, I think Griffiths does this also, which is kind of interesting. This little piece here, right, you have energy and momentum separate, right? If you don't like that, you can actually combine them together, right? Because energy and momentum together is just the 4 momentum, right? And this is actually known as the differential Lorentz invariant phase space, known as D-ellipse. The only reason that I remember this is because it's just a funny name, okay? And I'm going to try to stay away from this in this class, but Thomson does the derivation, so that's why I just want to show you that. So if you were to convert this to D-ellipse version instead, the 4 momentum version instead, you will just get a 4 momentum version of the delta function, right? And then the 4 momentum differentials instead, okay? Where this is imposing the conservation from the mass itself, because whenever you deal with 4 momentum, you're going to have E squared plus P squared equals M squared. Sorry, E squared equals to P squared plus M squared, right? And that's where these masks are coming from, okay? We're not going to use this, at least in this chapter. So just in case we need it in the future, I'm going to say, oh, I already talked about this, okay? All right. Any questions so far? I know I'm going through a lot of the chapter very quickly, but I'm just trying to skip through kind of like the important pieces that conceptually you need to know, but mathematically, Thompson does all this, most of the steps, and if you really, really want to be rigorous, you can fill in those algebra steps. Okay. It's very quiet, which is kind of scary to me. Any questions or concern before I go into like one example of decays? I'm actually going a lot faster than I thought it will. All right, with the remaining 14 minutes, let's do our first kind of like apply example, okay? So the next section in Thompson is particle decays. So it's a similar one in Griffiths, so you can actually see the parallel between them, okay? So just to let you know, some particles are unstable and they do decay, right? And this is the thing we've been kind of drawing where A is decaying into some particle 1 and 2. We don't even know what the particles are, okay? And what I want to show you guys is maybe the tau lepton decaying, right? So the tau in the table of all the particles, this is a subset of them, all 17 particles, this is just 8 of them, right? You have the tau, which is the heaviest charge muon, charge lepton, right? Where the lightest one is the electron, the next lighter one, the middle one is muon, and then you have a tau, right? That's the heaviest one, which is about 1.8 GeV in mass, okay? So what's going to happen is that these tau is going to decay into each of these lighter leptons or other things, actually, okay? And some of these decay modes are, let's say you have a tau decaying into a muon. So the Feynman diagram for that will be you have a tau coming in, right? And that tau decays into some W. And in order to conserve the particleness, you're going to have a neutrino tau coming out, right? Okay. And this W, right, if this is a tau particle, this will be a W minus in this case, right? Because the particle tau will have a negative charge, okay? And this W will decay into a muon and a muon neutrino, okay? And in this case, this is an antiparticle because it has to come into the vertex. Okay? So that's one way for the tau to decay. There are other ways for the tau to decay, right? Okay, because I'm going to highlight this, right? This W thing, right? Once you made a W, the W can decay into a lot of different things because it couples to a lot of different things, okay? Right. One of them, of course, is the muon and the muon neutrino, but it can also decay into an electron, right? If I just draw the same diagram, right? The W coming out, should have gave myself a little bit more space. It's not, draw that right there, right? This could have been an electron and a electron neutrino, right? Those are perfectly valid also. What's even more, right? That's what this is, okay? So the W minus, right, has a -1 charge total, okay? But like, for example, up quark has a charge of 3/2, right? Q of up quark has a charge of 3/2. So not 3/2, 2/3 upside down fractions, right? And then a anti-down quark has a charge of 1/3, right? Right? Okay. Since we're dealing with the W minus, we probably want the Q bar, which has a -2/3 charge. And then the D without the bar now has also a 1/3 charge. So this adds up to -1 as a charge, right? So the W could decay into this because it can conserve charge still, right? If it decays into an up bar and a down quark, okay? And then we'll see how this happens, okay? Same thing, right? The top line is still the same. You're changing into a tau neutrino, okay? But instead of this W decaying into a lepton, it could decay into a down, and then up. The up is going in because it's an antiparticle, right? And then the down is going up. Okay. Okay. This together is actually known as a pion. Oops. It's actually a pi minus. And these pi minus are known as hadrons. Okay. Not only does it decay into that, it can also decay into other types of hadron also, depending on how much energy is available to it. Okay. But this is one example. Okay. Ooh, go away. One example. Okay. Okay. Yeah. So if you go to the particle data group, so there's a website called pdg.lbl.gov. And then you look up like tau decay on that website or something like that, you'll find all the different possible decay channels you can go into. Okay. So the thing is, right, if you're starting as a tau up here, right, if you have a box, right, and then you started with 100 tau in that box, right, and then after like a nanosecond, you only have 50 taus now, right? You actually don't know what that tau decay into, right? You just know that you have fewer taus, right? Okay. So what's going to happen is that, right, each of these diagrams actually contributes to the decay rate of the tau. Each of these channels can contribute to it. Okay. 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 So, and each of these channels will give you what's known as a partial width of the decay. Okay. Remember this TFI thing we've been this thing we've been calculating, the transition rate, right? Okay. Another name for this is actually the width of the decay. Okay. Okay. Where, right, the total width, this is the total, right, is equal to the sum of all the possible ones. For the example of the tau, right? So one of these will be to the muon, right? Muon neutrino, oops, plus tau neutrino, right? You have to write down all the subparticles. The other part of the width is the electron neutrino, and then the tau neutrino, right? Another one is this tau to go away. Still the tau neutrino, and then the pion, right? Okay, but there's other processes that are also possible, but what they're going to do is they're going to lump all of this together as just hadrons, right? Remember, hadrons are the stuff that has to do with quarks, right? Anything that's made of quarks are called hadrons, okay? Right? So how does this total decay rate, or known as the width, this is the width of this decay, right? How does that have to do with what we're trying to calculate? Okay. So once again, right, if you don't like this arbitrary number, just think about you have 100 taus in a box, right? And the number of those taus changes with time, right? Because they're decaying. Okay. Right. And since these particles are decaying one at a time, and the probability of each of them decaying is the same, okay, what's going to happen is you're going to have some exponential decay where this factor in front here, this gamma, is the same gamma as we've been dealing with before, okay? Where N0 is the initial number of, taus that you have. If you start off with 100, that's 100, right? Where this is kind of like the decay width, the decay rate of, or width of that process. What's more typically used is actually 1 over that, where we're going to define something called the lifetime. Okay. Okay. Where it's just 1 over that. Because that's an easier thing to think about, because, well, if I wait 1 second, how many taus would I have left, right? This allows you to quantify that. Okay. Okay. So 1 over gamma is the lifetime. And what's even more familiar with most people is actually something called a half-life. right? So for example, like carbon decay, right, has a half-life of 5,000 years or something like that. And that's how they date mummies and stuff like that, right? It's the thing I learned from grade school, I think. The stuff we're dealing with is going to have a half-life much shorter than that, okay? Okay, we're talking about, so for example, I think muon has a half-life. Oh, I actually don't know what the half-life is. I know is lifetime is 2.2 microseconds, so you have to multiply by 1 over square root of 2 to calculate what the half-life is. Okay, but sorry, let me go back so that we're clear what we're trying to define here. There are 3 different things that are going to quantify the same thing. Okay, that might be the most confusing part, right? So you have the decay rate, which is this gamma thing, right? And then you have the lifetime, which is tau, which is just 1 over gamma, right? You also have half-life, which is basically the amount of time you wait until half your particle is gone. So if you start off with 100 taus in a box, how long does it take for you to get only 50? Okay, and then if you start off at if you mark that time at 50, right, another half-life goes on, you will get 25, and then you get like 12 and a half, right, and so on like that. Okay, and that's why this half-life is actually kind of nice to quantify things. Okay, and the relationship between tau, the lifetime, and the half-life is related to 1 over square root of 2 because, right, if tau, like if I put in t equals to tau here, right, if I waited one lifetime, right, let's say the lifetime is 2.2 microsecond, okay, if I wait 2.2 microsecond, that means t is actually equal to 2.2, right? You have e to the minus 1. If you punch that in your calculator, it's going to be about 0.37, okay? So basically, for each lifetime you wait, you're going to have 37% of your sample remaining, right? 37% is harder to memorize, so that's why people like the half-life, okay? Right, and therefore, you get each half-life, you get 50% of your sample remaining instead, right? Okay, so but in this class, we're going to be dealing with lifetime and the decay rate instead, okay? But this is just to connect things back to what a lot of other sciences might be using, okay? All right, so I think this is actually a good, should I show you this right now? Yeah, let's just finish up this section, okay? So each of the diagrams, remember I was drawing all these different tau decay diagrams, right? I'm not going to draw the details, right? So you had one that decay into mu and the mu neutrino, right? You have one that decays into electron and electron neutrino, and you have some that decays into pions, right? Charged pions and a neutrino, right? Each of these you can actually look up, right? The particle data book has it. You even find it on Wikipedia, okay? Okay. So about 25.5% of the time, the tau actually decays in this mode, right? Where you decay into either a neutral or a charged pion, okay? That's what this pi is, right? And then the tau neutrino, okay? 10%, well, 11% of the time, it decays into a charged pion and a tau neutrino only. So I think maybe this process up here is actually the second one, right? How we do the first one then? Oh, okay. Sorry. Okay. This first one, I'm gonna guess. Okay, So this first one here is actually the tau decaying into W first, right? You always get that. Okay, and it says a charged pion and a neutral pion at the same time. Okay, so what we're trying to produce, right, is a let's say the anti-up quark, right, and a down quark, right? And what happened is that you have an anti-down quark and then an up quark here, And this actually creates a neutral pion instead. Okay, pi 0 instead. Okay, I'm gonna look up this diagram actually. And because it's surprising to me, actually, this is I thought this was the right one. This is actually the most probable one, right? Okay, it's actually 25.5%. Okay, but all of these combined together are what's known as hadronic decays. Usually they're lumped together. Okay, the other fraction, right? You can see down here are the neutrino to electron, right? And it's very, very similar to for the tau to also decay into a muon. So the tau doesn't care, almost doesn't care, whether or not it's decaying into electron and muon, okay? And this is going to bring up a concept called lepton universality in a little bit, okay? Universality. Okay, I can't spell it. There's an A here somewhere. Oh, I think I switched the A's and the I. Okay, you know what I mean? The marker is just a little bit too thick. I'll write it correctly, okay? But so whenever you see numbers that are the same as each other, right, that brings up something interesting, right? That means there's some sort of symmetry that's causing that to happen, okay? Okay, so that's all I have. Is there any questions? I'm just going to try to spell universality, okay? Any questions before we end the class today? I'll stop recording.